In this lesson, we'll discuss radian measure. Radians are an alternate way of measuring the size of angles, similar to how degrees measure the size of angles. We saw in an earlier video how there's actually many different types of measuring the size of angles, but radians and degrees are the two that we use predominantly in trigonometry. Radians are important because they're a unitless measure. So when you're speaking in terms of degrees, you have to say 280 degrees, 19 degrees. You have to indicate that you're referring to degrees. It's not necessary to indicate that you're referring to radians because technically there's no unit of radian. It's just a single number. We often do say the term radian after how large we're indicating an angle measure is, but again, it's not necessary. If you place the vertex of an angle at the center of a circle and open the angle to a point where the intercepted arc length is equal to the radius of the circle, then that angle is equal to 1 radian. So that's kind of a mouthful. Let me show you a diagram here. So I have a circle and an angle measure oriented right at the center of that circle. So here's the center of my circle. This angle measure I will call theta. The radius can be described, as this distance here. So it's the distance from the center of the circle to some point out here on the circle. Now, that angle measure intercepts an arc length. That arc length is there. We generally refer to arc length with the lowercase letter s. So when I have the radius equal to the arc length, then that is defined as 1 radian. That's what that definition tells me. So for instance, if I were to take this line and rotate it a little bit further, alright, so let me readjust my diagram here. So this length here in green is my radius. Of course, this is still my angle measure theta, but my arc length is now a little bit larger. In fact, it's not quite the length of the radius, but it's pretty close. So I'm not quite to 1 radian yet. If I continue rotating that a little bit further out, so let's say to right there. Okay, now I have to erase this, I'm sorry. Here's the arc length of the circle. Here's the radius. Those two lengths are approximately the same now. So what that means is this angle measure theta is now equal to 1 radian. And that's how we define radians. Let me show you an applet now that might help to make this a little bit more clear, and it's something that you can work with at home. So this applet basically allows me to do the same thing. I'm just able to drag the point P to wherever I want on the circle. It tells me the measure in radians of this angle theta rotated from the x-axis. It also tells me the arc length. So this arc length right here is the distance from the x-axis up to P. And it also tells me the radius of the circle. And the radius is always going to be 5 unless I change the radius. And I can actually change the radius by moving this point. But for right now, I'm going to leave the radius at 5. Alright, so let me get rid of all this extraneous stuff here. You'll notice that arc length is slightly less than the radius. So I don't have 1 full radian described yet. But if I move point P along a little bit further until the arc length is equal to 5, or as close as I can get to 5, then I end up with 1 radian. So this is the definition of 1 radian. If I want 2 radians, I can continue moving this point around until my arc length is basically double. So at 10, then I end up with 2 radians. 3 radians, you might think that 3 radians would be back to the x-axis. But my arc length in this case would need to be 15, or as close to 15 as I can get it. And then the radians is 3. It's not quite back to the negative part of the x-axis. In fact, it turns out that when you get back to the negative part of the x-axis, your radians is equal to 3.14. And I can't quite get it exactly there, but that's okay. So the radians for the quadrantal angle that's equivalent to 180 degrees is pi. That's what we come up with. And actually, if you continue rotating all the way around, you eventually get to 2 times pi, 6.28. Interesting thing that I'll mention here. So pi is approximately 3.14, which is a very useful number in mathematics. But there is some movement these days to, instead of using pi, it makes things a lot more convenient to use tau. And so tau is defined as 2 pi. So tau looks like this, but it's equal to about 6.28. So it's exactly 2 times pi. But there's a lot of convenient things that work out when you use tau instead of pi, although it's not very widely adopted at this point. Now, what's interesting about radian measure is it's independent of how large your circle is. So let me rotate around until I have 1 radian again. So I'll get as close as I can to 1 radian. If I change the radius of my circle, the radian stays the same. The radius is changing, but the arc length is changing at the exact same rate. So this angle measure, theta, is always going to be 1 radian, no matter what the radius of my circle is. So if I bring the radius of the circle down, if I increase the radius of the circle, 1 radian is always the same angle measure regardless. Converting between degrees and radians. The circumference of a circle can be found using the commonly known formula from geometry, c equals 2 pi r. So the circumference of a circle is 2 times pi times the radius of the circle. Since this measures the distance around a circle, which is 1 full revolution, we can assume that a circle of radius 1 has 2 pi radians in 1 full rotation. Thus, 360 degrees, which is 1 rotation of a circle in degree measure, is equal to 2 pi radians, which is 1 full rotation in radian measure. So to convert a measure in degrees to a measure in radians, we basically take this ratio and just reduce it. So if, for instance, if you divide both sides by 2, the 2's cancel out on the right-hand side. 360 over 2 is 180 degrees. So that's kind of where we're getting this ratio, pi over 180 degrees. So we multiply by pi over 180 degrees. That'll take a measure that's in degrees to start with and change us into radians. Similarly, to convert a measure in radians to degrees, we multiply by 180 degrees over pi. Or a lot of times it's actually easy to just substitute the symbol pi for 180 degrees, simplify that fraction, and that can make your work a little bit easier. So let's look at some examples. Convert the following angle measures from degrees to radians. Starting with 45 degrees. Now, what I used to struggle with in trigonometry was, when do I multiply by pi over 180 and when do I multiply by 180 over pi? Well, I'm going to take a short trip here into what's called dimensional analysis, and if you understand how dimensional analysis works, you'll never make this mistake. So, for instance, when you are working with dimensional analysis, you're changing one unit of measure to some other unit of measure. So if I want to change 45 degrees into radians, well, the thing is, I need to multiply this by some fraction that cancels out the degrees. Because when it comes to dimensional analysis, the units of measure can cancel similarly in the same way that numbers can. So if I want the degrees to cancel out, I need to have degrees in the denominator so that this degree measure will cancel. In order for that to happen, I would need degrees in the denominators, radians in the numerator. So I know that there are pi radians and 180 degrees. So the only unit that's left is radians, which means all I need to do is just reduce this fraction, and that's going to tell me what the equivalent angle measure is in radians. Now, 45 times 2 is 90, which means 45 can actually go into 80 4 times. So this is equivalent to pi over 4. That's the exact measure in radians. Sometimes you can get away with using approximate answers in radians. Most of the time you need to use exact answers. So as fractions with pi in there. Let's try another one. 120 degrees. So again, if I want to take 120 degrees and I want to get rid of the degree, then what I need to do is multiply by something that has degrees in the denominator and radians in the numerator. So there's pi radians in 180 degrees. So the degrees will cancel. Then I just have to reduce, 120 over 180. So if I divide both by 10, the zeros will go away. Both of these have factors of 6 in them. 12 over 6 would be 2, 18 over 6 would be 3. So this is 2 pi over 3. And we can say 2 pi over 3 radians, or we can just say 2 pi over 3. It's perfectly fine to leave off the unit because this is a unitless measure. All right, negative 65 degrees. Certainly, if you have something that is not within the bounds of 0 to 360, or as you'll get used to in radians, 0 to 2 pi, your final answer needs to be, you need to find a coterminal angle. You want the simplest form of your answer in the end. For most of you, it's probably easier if you're starting in degrees to get that coterminal angle in degrees first, and then switch over to radians. It's up to you how you want to approach that, but that's what I feel is easiest. So for negative 65 degrees, to get something coterminal with that, I'm going to add 360 degrees, which gives me 295 degrees. Now the 295 degrees I want to convert to radians, so I'm going to put the 180 degrees in the denominator so that the degrees cancel, the pi in the numerator. So the degrees cancel, then 295 over 180. So that I do know both of those would divide by 5. So let's see what happens when I divide those by 5. So 295 divided by 5. That's 59. So 59 pi over, and then 180 divided by 5 gives me 36. And that's not reducible. Neither one of those share a common factor. So that is the final answer. Okay, the last one. 220.318 degrees. So this one is starting out with an approximate value. It has a decimal, so you can end with a decimal. You don't have to finish off with pi in the end. So to convert this, just remember 220.318 in degrees. You want to multiply it by something that has degrees in the denominator, so that's where your 180 is going to go, and then the pi in the numerator. Now, when we use the calculator here, let me bring the calculator over so we can use it. What I'm going to do is I'm going to take 220.318, multiply that by pi, so second and the caret gives you pi, and it's still an approximation to pi, but it gives you 9 decimal places instead of just usually 2. So I would recommend using that for your calculations. And then we divide that result by 180, and the result here is approximately 3.85, and that's a number of radians. Next up, convert the following angle measures. How about angle measures in radians to their equivalent degree measures. So I have pi over 6. So this is in radians to begin with. Now, what's nice when we are working with these exact angle measures that have the pi in them, you're not going to have, it's not that you couldn't, it's just not going to be customary to have pi in a measure for degrees. So you can kind of use this same sort of logic in order to decide how to change this into degrees. So you have to multiply it by a fraction, and you want the pi to go away. So the pi is going to go in the denominator, and leaving you 180 degrees in the numerator. So the pi's cancel out. You have 180 over 6, and 6 will actually go into 180 30 times. So this is equal to 30 degrees. And notice now I do have a degree mark on here because there was no, the only degree in here was the 100, in this calculation, was the 180 degrees. So my leftover answer has a degree in it. Now, that works. An alternate method, when you have the pi in your measure and you want to convert to degrees, if you just change the pi into 180 degrees and reduce that fraction, then that will change it into degrees as well. So 3 goes into 180 60 times. So 2 times 60 degrees is 120 degrees. So that's our equivalent angle measure in degrees. Part C, negative 5 pi over 4. Negative 5 pi over 4, certainly in our final answer, we want to make sure we answer, with the coterminal angle that's in the range of 0 degrees to 360 degrees, or 0 to 2 pi as the case may be. Now, I'm going to make it into degrees first before I make that conversion, because generally it's just easier to work with degrees because often you have whole numbers rather than fractions. So I'm going to make my conversion first. Negative 5 times 180 degrees over 4. So 4 goes into 180 degrees 45 times, and then negative 5 times 45 is negative 225. So that's the equivalent angle measure, but I want to give my final answer, that's coterminal. If you are supposed to do this in your homework, that'll be specified, but just follow the instructions given. Now, to get a coterminal angle, I'm going to add 360 to this. I'm going to take 360 essentially minus 225. I get 135 degrees. So this results in an angle measure of 135 degrees. All right, 1.2125. Now to make this, there's no value of pi in this number, so I can't just change the pi to 180. I really do have to do the calculation. So 1.2125 times, in the end I want to have degrees left over, so I want my degrees in the numerator, which means pi is going to go in the denominator, the 180 in the numerator. Let me make that pi a little bit nicer. Now, since we started with an approximation, it's fine to end with an approximation. So I'm going to get the calculator out, and we'll do that. All right, so 1.2125 times 180 divided by second pi. And I get 69.47 degrees. And again, follow rounding rules in your homework, but I'm just choosing to round to 2 decimal places here. Now, there are many common angle measures that we're going to work with throughout the study of trigonometry. And you're going to want to know those common angle measures pretty well, and it's good to just kind of get a chart of all the different ones that you're going to have. So starting in degrees, we'll start there, and then we'll convert to radians afterward. So first, quadrantal angles are really important. So we have a 0-degree quadrantal angle, a 90-degree quadrantal angle, 180-degree quadrantal angle, and 270. So those are the quadrantal angles. Those are really important to know. 360 I'm not going to list because that's equivalent. It's coterminal with 0. All right, now we also learned special angle measures based off of 45-45-90 triangles and 30-60-90 triangles. And those are the other angle measures that are here. The ones in between, halfway through, those are your 45-degree angle measure changes. So like the next 45-degree angle measure would be 90 plus 45, which is 135. So that's the equivalent of a 45-degree angle measure in quadrant 2. So if you go 180 plus 45, then that gives you 225 right here, and 315 in quadrant 4. Okay, then the 30 and 60 degree angle measures. This would be 30 degrees and 60 degrees. Likewise, if you go 30 degrees past 90, you have 120 degrees, and 60 degrees past is 150. 30 degrees past 180 is 210, and then 240 for 60 degrees past. Keep doing that. 240, I need a 0. 30 degrees past 270 is 300, and 60 degrees past is 330 degrees. So these are the most important angle measures that we're going to work with in degrees. Alright, now for radian angle measures, let's begin with quadrantals as well. Those are generally fairly straightforward. So 0 degrees is equivalent to 0 radians. And 180 degrees is equivalent to pi radians. Halfway in between that is 90 degrees. So it should make sense that 90 degrees is equivalent to pi over 2. Now if you take pi plus pi over 2, then in order to make that work, you have to get a common denominator. So it would be 2 pi over 2 plus pi over 2 is 3 pi over 2. That's the equivalent of 270 degrees. So 3 pi over 2. And that's really kind of the thing that makes radians undesirable for students to want to work with, is because you often have to work with fractions. But those, if you just kind of get used to, can help you out. You don't really have to work with a lot of fractions if you just remember what the common ones are. Alright, now all of the measures of 45 degrees are pi over 4, because if you take 180 degrees divided by 4, that gives you segments of pi over 4. So if you take pi, if you want to figure out what the pi over 4 angle is in quadrant 2, take pi over 2, which is 90, plus pi over 4, which is, 45, and that's going to give you 3 pi over 4. Just working with fractions, you'll get 3 pi over 4. So that's the equivalent to 135 degrees. Or in quadrant 3, it's 5 pi over 4. And in quadrant 4, it is 7 pi over 4. For 30-degree angle measures, the equivalent is pi over 6. For 60, it is pi over 3. In quadrant 2, we have 2 pi over 3, equivalent to 120 degrees, and 150 is 5 pi over 6. 210, if you convert it, it would be 7 pi over 6. And 240 would be 4 pi over 3. 300 is 5 pi over 3. And 330 is 11 pi over 6. Those are all the important ones. When it comes to testing, it's going to be advantageous for you to create a circle like this that has all these common angle measures and conversions. It's really going to be a big time savings to you. In a few sections, we'll see some other things that we want to put on here that are important. But for now, the conversions between the degree and radian measure for the common angle measures is really helpful. Now, one way of doing that to make sure you can do this quickly and easily, because it might seem a bit overwhelming at this point. If you change everything to 15-degree angle measures. Alright, to get 15-degree angle measures, think about this. So if I added in a line here for 15 degrees, and added in a line here for 75 degrees, you don't actually need these. These aren't the common ones, but what that does is it makes all of the spacing even. So all the spaces between the common ones are now 15 degrees. This next one here would be 90 plus 15, which is 105 degrees. And this last one right here would be 150 plus 15, so 165. I'm putting them in red because, again, they're not ones you need, but they can be helpful. And here's why. So that gives you 12 even spacings of 15 degrees. So what you can do is just start writing 0 pi over 12, 1 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, 6 pi over 12, 7 pi over 12, and so forth. And you can keep going around the entire unit circle, but I'm not going to go any further than that. Now, if you reduce these, 0 pi over 12 is obviously 0. This would just be pi over 12, although it's not one of the angle measures we need. 2 goes into 12 6 times, so this is pi over 6. 3 goes into 12 4 times, this is pi over 4. 4 goes into 12 3 times, this is pi over 3. So these will reduce to the measures that you do need. The only thing you have to think about and make sure you remember to do is add in those angle measures that are multiples of 15s, because if you don't put those in, your measures are going to be all off. So that might be something that can help you while you're testing, help you get these common angle measures very quickly. Lastly, we're going to talk about arc length. If an angle theta is measured in radians, then the length of an arc of a circle whose radius is r, intercepted by theta, is s equals r times theta. And the important thing is that theta be measured in radians, because in radians we define things in terms of the ratio of the radius to the arc length. So if we know the radius and we know what theta is, we can calculate our arc length using that. This does not work in degrees. However, if you're in degrees, you can always convert to radians first and then do the formula. So for example, find the length of the arc intercepted by the given central angle in the figure to the left. So the angle measure theta that's provided is 3 pi over phi. And the radius that's provided is 14.7. What we're attempting to come up with is this distance here, which is s, the arc length that's intercepted of the circle. We're told that we can calculate this by taking the radius of the circle times the angle measure theta. So the radius of the circle is 14.7, and angle measure theta is 3 pi over 5. And since we have a decimal value in the calculation, I'm going to just give a decimal answer rather than answering in terms of pi. So we'll get the calculator out, and we'll calculate 14.7 times pi, times 3 pi. Well, hit the right button there. Times 3 pi over 5. So 27.7 is what I'll answer with. And that's going to be the length of the arc that's intercepted. How long is an arc intercepted by a central angle of 65 degrees in a circle of radius 21.68 centimeters? Well, again, the arc length is the radius times theta. The only issue is theta needs to be given in radians and not degrees. So I need to convert that. So I'll say 65 degrees times, I want the degree to go away, so I'm going to put the degree, the 180 in the denominator. And it doesn't specify that I need exact answers, so I'm just going to, multiply and approximate the value of pi. So let's see what happens here. I'll move my calculator so I'm not covering my solution. 21.68 times 65 pi over 180. And I get 24.6. Well, since I had two decimals to start with, well, I guess it would be 24.60. And it was measured in centimeters to start with, so I'll answer in centimeters. So if you'll notice, the arc length is fairly close to the radius, and that's because 65 degrees is actually pretty close to 1 radian. 1 radian is going to be, if we calculate it, I can show you what that is. In order to do that, we just use our conversion, 180 divided by pi, and that leaves me with a measure in degrees that's equivalent to 1 radian. So about 57.3 degrees is equal to 1 radian. So that's why the radius and the arc length was fairly close to one another, because 65 is actually pretty close to 57 degrees.